Hey everyone, Simone here. Today we're diving into the world of Schmitt Triggers, tiny circuits that solve big problems in electronics. They're like the superheroes of signal processing, rescuing your circuits from the clutches of pesky noise. In simple terms, a Schmitt trigger is a special type of circuit that switches its output between two states, high and low. But here's the cool part. It doesn't switch at a single voltage level like a regular switch. Instead, it uses two different voltage thresholds, one for switching high and another for switching low. This unique characteristic is called hysteresis, and it's the secret sauce that makes Schmitt triggers so awesome. It's like having a gatekeeper that only lets strong, clear signals through while ignoring the weak and noisy ones. Whether you're building a sensitive sensor system or a robust power supply, Schmitt triggers are your best friends when it comes to cleaning up noisy signals and making your circuits more reliable. So buckle up as we explore the magic of hysteresis and uncover the secrets of these tiny but mighty circuits. Imagine you're trying to listen to your favorite song on a staticky radio. The music keeps fading in and out, making it hard to enjoy. That's what noise does to electronic signals. It disrupts them and makes them unreliable. This is where Schmitt triggers come in with their secret weapon, hysteresis. Think of hysteresis as a safety margin that prevents the trigger from switching erratically when the input signal is hovering around the threshold. Let's say the input voltage is slowly rising. A regular comparator would switch its output high as soon as the input crosses the threshold voltage. But a Schmitt trigger with hysteresis won't switch until the input goes a bit higher than the threshold. Similarly, when the input voltage falls, the Schmitt trigger won't switch back to low until the input goes a bit lower than the threshold. This creates a hysteresis band, a region where the output remains stable, even if the input signal is noisy. Schmitt triggers are like the clean energy enthusiasts of the electronics world, especially when it comes to power supplies. They help create stable and efficient power sources that keep your gadgets running smoothly. One common application is in voltage regulators, which ensure a constant output voltage regardless of fluctuations in the input voltage or load current. Schmitt triggers act as the brains of these regulators, monitoring the output voltage and adjusting the current flow to maintain a stable output. Another crucial use is in oscillator circuits, which generate repetitive electronic signals like clock pulses for microprocessors. Schmitt triggers provide the necessary switching action to create these oscillations, ensuring accurate and reliable timing for your digital circuits. But wait, there's more. Schmitt triggers also shine in power-on reset circuits, which prevent your devices from going haywire during power-up. They hold the system in a reset state until the power supply stabilizes, ensuring a smooth and predictable startup process. To understand how Schmitt triggers work their magic, we need to peek under the hood and see what makes them tick. And guess what? It all comes down to transistors. Transistors are like tiny electronic switches that can amplify or switch electronic signals. They're the fundamental building blocks of countless electronic circuits, including Schmitt triggers. A simple Schmitt trigger can be built using just two transistors arranged in a clever configuration called a bistable multivibrator. In this setup, the transistors are connected in a feedback loop, where the output of one transistor controls the input of the other. This feedback loop creates the hysteresis effect we talked about earlier. When one transistor is on, it forces the other one off, and vice versa. This creates the two stable output states of the Schmitt trigger. Section 5. Building a simple Schmitt trigger circuit. Alright, enough theory. Let's get our hands dirty and build a basic Schmitt trigger circuit using transistors. Don't worry, it's easier than it sounds. For this project, you'll need two NPN transistors, for example, two N3904, two resistors, for example, 10 kilo ohms, one variable resistor, for example, 100 kilo ohms, a breadboard, jumper wires, a power supply, for example, 5 volts, and a multimeter, which is optional. First, connect the positive rail of the power supply to the collector of the first transistor, Q1, and the base of the second transistor, Q2. Then connect the emitter of Q1 to the emitter of Q2 and to the negative rail of the power supply. Next, connect one end of the first resistor, R1, to the base of Q1 and the other end to the positive rail. Similarly, connect one end of the second resistor, R2, to the collector of Q2 and the other end to the positive rail. Finally, connect one end of the variable resistor, VR1, to the base of Q2 and the other end to the negative rail. This variable resistor will act as our input voltage source. Section 6. Schmitt Trigger versus comparator, a head-to-head. Now you might be wondering, hey Simone, how are Schmitt triggers different from those comparator things I've heard about? Good question. Both Schmitt triggers and comparators are electronic circuits that compare two input voltages and produce an output based on the comparison. However, there's a key difference: hysteresis. Comparators are like simple referees. They make a decision based on the current input voltage. If the input voltage exceeds a certain threshold, the output switches high. If it falls below the threshold, the output switches low. Simple, right? Schmitt triggers, on the other hand, are like referees with memory. They consider not only the current input voltage, but also the past history of the input signal. This is where hysteresis comes in, providing that noise immunity we talked about earlier. So when should you use one over the other? If your application requires clean and reliable switching even in noisy environments, Schmitt triggers are the way to go. But if you need fast and precise voltage comparisons without hysteresis, comparators are the better choice. Section 7. Real-world applications of Schmitt triggers. Schmitt triggers are like the unsung heroes of the electronics world, quietly working behind the scenes in countless devices we use every day. Let's shed some light on their real-world applications. Touchscreen devices. Ever wondered how your smartphone knows when you've touched the screen? Schmitt triggers. They detect the tiny changes in capacitance when your finger touches the screen, triggering the desired action. Thermostats. Keeping your home cozy is no easy feat, but Schmitt triggers make it a breeze. They regulate the temperature by switching the heating or cooling system on or off based on the room temperature, ensuring a comfortable environment. Line drivers and receivers. In long-distance communication systems, signals can get weak and distorted. Schmitt triggers act as signal boosters, cleaning up the received signals and ensuring reliable data transmission. These are just a few examples of the many applications where Schmitt triggers shine. Their noise immunity, stability, and versatility make them indispensable components in a wide range of electronic systems. Section 8. Advantages and disadvantages of Schmitt triggers. Like any good superhero, Schmitt triggers have their strengths and weaknesses. Let's weigh the pros and cons of these versatile circuits. Advantages: high noise immunity. Hysteresis makes Schmitt triggers incredibly resistant to noise, ensuring reliable switching even in electrically noisy environments. Improved signal integrity. By cleaning up noisy signals, Schmitt triggers help maintain signal integrity and prevent false triggering. Wide range of applications. From simple oscillators to complex control systems, Schmitt triggers find applications in various electronic circuits. Disadvantages: limited speed. The hysteresis effect introduces a slight delay in switching, which can be a limitation in high-speed applications. Potential for oscillation. In certain configurations, Schmitt triggers can exhibit unwanted oscillations if not designed carefully. Increased complexity. Compared to simple comparators, Schmitt triggers add a bit of complexity to the circuit design. Despite their limitations, the advantages of Schmitt triggers far outweigh their drawbacks, making them invaluable components in many electronic applications. Section 9. Conclusion: Schmitt triggers. Small circuits, big impact. So there you have it. A crash course on Schmitt triggers, the noise-busting superheroes of the electronics world. We've explored their inner workings, their applications, and their strengths and weaknesses. From cleaning up noisy signals to ensuring stable power supplies, Schmitt triggers play a crucial role in making our electronic devices more reliable and efficient. Their ability to provide hysteresis, that magical noise immunity superpower, sets them apart from simple comparators. So next time you're tinkering with an electronic project and encounter a noisy signal, remember the mighty Schmitt trigger, a small circuit with a big impact.